doesn't listen. Okay. So if you need help from other people, you just need to give them the credit. Okay. Do not stuck there forever. You will feel frustrated. So you are not getting the most from this class. All right. Yeah. Let's help each other to get through everything in this class. Let's take a look at the part 2 of the tutorial. I think I went through the interrupt in the microcontroller class, did I? For you guys, for group 2? So that's timer 2. I mean, can do the same job, but the only difference is the timer 2, I think, is only 8-bit. The timer 1 is 16-bit. So for a matching number, you couldn't use anything larger than 2 to the 8th, I think. But for if you are using timer 1, so the maximum number to count to should be 2 to the 16th. And they are the same technique by shifting that bit. By shifting 1 by how many bits, so you can set this bit in the register. I mean, really no difference. It's very simple. But here's one thing I probably want you guys to really know what's going on here. This one. So that is a frequency of triggering the ISR. Do you agree with that? You still remember this equation? Any of you? It's just in the data sheet. Okay, just follow. And apparently, let me write on the paper first. FOCNX equals to this times N times 1 plus OCRNX. So here is so that is the equation to define the frequency of triggering the ISR. So how frequent you want to trigger the ISR. And so the clock frequency definitely 16 megahertz for your Uno board, right? Or nano, doesn't matter. And N is a prescaler. So take a look. You can set it up in the register. So what's N here on the website? Take a look. Back to the website and take a look. Prescaler, what is that? So it's 8. And I found a typo on their data sheet. Shame on them. So CA22, CA21, CS20. Come on. There should be CS22, CS21, CS20, right? I hope I'm correct, but this is very rare. This is what they are selling, the product, and they have a typo, but they are not trying to fix it. I don't know. If I'm wrong, let me know. But I think it should be CS. It should be consistent, right? So that's the CS. The 3 bits for CS is a clock select, so it's making sense. So it's CX. And CS2, right? CS2 to 0, so 3 bits. And so what are the 3 bits you assign to these 3 binary spots will determine the prescaler. And keep in mind, the prescaler is not going to set up the frequency to be 16 megahertz divided by 8. So it's just giving you this number 8 for the equation. So let's take a look at the code, see if we are setting up 8 over there. Take a look. Is that 8? Is a prescaler, which is N, capitalized N? Is it 8 or not? Yeah, and the middle one, right? Is that the middle one? Did we shift CS2, CS2 to CS20? Tara, did you get it? Did you get this? So take a look. Okay, yeah, no worries. So look at this. You guys did interrupt in junior design, did you? Okay. But it's fine if you forgot it, right? And I think we had a lecture last week or early this week. I forgot. Probably last Friday. We talked about the interrupt in 351 again. So there are 3 timers in the microcontroller in the Uno in the 328P timers. Did you design any timers in logic? Counter? Pretty much the same thing, just counting, right? Since you know the clock frequency is 16 megahertz, so if you design a counter, it's going to be a timer. Since you know every count is 1 over 16 mega, so you know how many counts will be 1 second. That's how you can design a digital watch, because you know it's 16 megahertz. It can it's not being connected to anywhere, right? It's just like running independently by itself. So just asked a very good question. I didn't understand that by that time. I mean, during the class. So when we were talking about the sensor actuators, he asked about the SkyCard, the door latch for scanning. So you were asking how that device can know the time period without being connected to a Wi-Fi or router. Do you think it's being connected to Wi-Fi? I don't think so. Yeah, I don't think so. I don't think it's Wi-Fi. I don't think there's Wi-Fi there, because if we are out of Wi-Fi, we can still open the door. But you mean updated? So here's one. Yeah, but here's one thing. I think it is able to code itself without being updated from a server or from a Wi-Fi signal. Or if someone want to update it, want to program it, update the firmware inside, they can open the lid and plug in a cable to do it. But is there any way, like without connecting that guy to a Wi-Fi, but we can still use it and give a different customer, different users a different time period and different access in the building? There's so many these locks, and we can assign, for example, Tyrone just access to these 3 labs, but no others. And within this time period, it's going to expire at a certain period. And also, it only available. You can only access the lab from 6 a.m. to midnight. Think about it. If you're the engineer, how do you design it? Huh? Yeah, a built-in clock. That's pretty easy to make as long as it's being powered up. So it's always counting, right? Um, yeah, I think it is. It can be synchronized when it's being manufactured, and when they ship that guy out, they don't need to power it off. So the battery is embedded. They always been powered up, and I don't think it's consuming a lot of power. I think it's fine. Um, but if in the future it's out of power totally, I think they will have to replace the battery. But I'm pretty sure there's a backup battery. So whenever the main battery is out of juice, it's gonna create an alarm. So even though it's alarming, but also there's a backup battery there, not letting you know, it's still supporting the clock to run. So when after you replace the main battery, then it won't use the backup one. But I think the main battery, the new battery probably will charge up the backup one. So you always have a backup. So the clock will not stop, right? So that's one solution definitely you can figure out. So what about the time period? What about the like only from this academic year, from September 2020 to May 1st of 2021, and only from 6 a.m. to midnight? Remember the RFID, your Sky card? There's no battery inside, right? No battery. It has a coil, so whenever you put it on the programmer wirelessly, it's going to be wirelessly charged, and a code will be sent, or the main device will program your Sky card after it's being powered up by the coil. So definitely depends on the programmer. I mean, I don't know the details of the code, but definitely you can send, the programmer can send a specific code to the card as a ID, temporary ID, before it's being overridden. And part of the code must define something. So part of it can define the time frame every day, and also the expiration date, and also the access to different rooms. So every time you scan it over here, it's going to try to match if everything is 100% matched, and make a decision if it should give you access to the room. Yeah, and I think there's a code in the RFID after it's being programmed, and that single code contains all the information in there. Or it can be a different level. It's checking the first one first, and then the second one. If that one matches, then the second one, the second level, third level. Um, but I don't think it should be. It has to be connect to the wireless internet or cloud. Okay, let's come back to the interrupt. Um, so there's a control register for the interrupt. It's just the memory, 8 bits, right? It's all the registers are 8 bits in your 328P microcontroller. It's an 8-bit CPU. And so every byte in there, so that's 1 byte for this register. It's just called TCCR2B. So time and counter, right? So timer counter controller register, I think that's what this one stands for. 2. So that's not 0, not 1, it's 2. Because there are 3 timers, 3 different hardware sites in the CPU. So there are different logic blocks, right? So timer 0, timer 1, timer 2. There are 3 different hardware. And that's timer 2. And that's the register B of the timer 2. And so there, the very last 3 binary bits will define the prescaler. Right? That's it. So it's going to define the value of the prescaler being used in the equation I showed you here. You really don't need to think about that much. Okay. So here's a prescaler, which is 8. If I set CS21 to 1, but not set the other 2 bits, it's going to be 010 for these 3 bits. Did you get it now? We don't want to lose anybody. Did you get it now? So the purpose is to set up, not set up these 3 bits in this register. Don't think about that much. I mean this can be a little bit confusing. So the purpose is to, you don't need to think about that deep, right? So you are the user, you bought it, you just use it. You don't need to think about the logic behind it. So the purpose now is just to configure these 3 bits. Boom, boom, boom. Yeah, because this is like a control register. It contains the information for your interrupt. So you just put a 1 here and do not care about the other 2 bits. So it's going to be 0, 1, 0. And now you look at the table here. 0, 1, 0 will define the press together to be 8. That's it. Done. So we get a n number. So the n here, which is 8. And you know this is given from the crystal, which is 16 megahertz. So 2 times 8, and you have 16 mega on the top, and 1 plus something. So this is something you want to program. You want to put in your code as a constant. And now this time, for the car project, we don't know this number yet, but we know how often we want to trigger the interrupt. I will let you know how often. Okay, it doesn't have to be that, but it's working. So this one should be 20 microseconds. What I mean? If you have your main code for the 2-wheel car, setup and loop. How long is the loop? How long is the loop? 4 milliseconds. Right? We did it yesterday, Wednesday. God, it feels like this yesterday. Time flies. I still remember last Friday, James said like, have a good weekend, and now it's Friday again. He was asking for the driver, and goodness, all right. So the loop is 4 milliseconds. We did a calculation. Just look at the notes on video, okay, on Wednesday. The way we made 4 milliseconds for the loop is we have a loop timer variable and microseconds function, right? We directly plus 4,000 microseconds to set up the standard loop time to be 4 milliseconds. So the loop will be 4 milliseconds. And we are defining the ISR's frequency is 1 over 20 microseconds, which means every 20 microseconds, it's going to go to the ISR and do something. Okay, so for the design here, the loop is doing the PID controllers in the loop, because you do need that position checking and adjustment to happen more frequently in the main loop. Keep calculating the PID errors. But if you compare 4 milliseconds to 20 microseconds, so 4,000, which is 4,000 microseconds to 20 microseconds. So it's going to be interrupted pretty often. It doesn't matter because the computer can handle that. So what it's actually doing is, it's not able to finish one loop, but it will be interrupted for a few times. So what I put, or what that guy put in the interrupt is the driving code to actuate the wheels. So it's like this, right? If I slow down everything, that's a loop, okay? Here's the driving circuit. The driving circuit can be executed really quickly. It's being triggered every 20 microseconds, but the time is spent over here, I don't know, can be less or more, but I think it's somewhere, I don't know, I actually don't know. It doesn't matter. It should be super quickly because it's really quick. Just assign all the digital bits to the wheels. So here's the main loop, right? It only after 20 microseconds, then go to the ISR, move the wheel, and come back. 20 microseconds, move the wheel. Keep doing this. All right. You don't have to update the PID error really quickly, as long as you have your wheels is moving, so the car will not tip over, because you always have something is moving. If the wheels are not moving, then it's gonna fall over or whatever. So it's gonna hold the previous PID's value before you get a new one, and then it's gonna keep doing that. And after it gets the PID error updated in your main loop, so it knows the new position, and whenever it get interrupted again into there, so it's gonna rotate the wheels again, using the tool, use a new PID errors value. So that's a strategy, because you really want to keep your wheels activated more often compared to the loop itself. So it seems like the wheel is always rotating, but actually it's not. It's only being updated every 20 microseconds. Any questions or any thoughts? Because it's being executed really fast, right? If you are thinking about the real world, it just sounds like impossible. Yes. And here's another point. We'll do a calculation. I think I have that over here. So this is the frequency of the signal to trigger ISR. Let's see, here's one thing you need to know. Okay, so for this frequency, this trigger signal, triggering the ISR, so both the rising edge and falling edge will activate the ISR. So after this calculation, let's see, 16 megahertz on the top, and 2 times 8 times 1 plus x. Because I'm trying to program it, but I don't know what is x. So I need to assign this number to that variable. And for the frequency here, remember I just mentioned, both the rising edge and falling edge will trigger the ISR. So the frequency as the period here should be 40 microseconds rather than 20 microseconds. I do need, okay, something like this. Rising edge, falling edge. I need the ISR to be triggered for every 20 microseconds, right? That's how that works. Because after 20 microseconds, I get a rising edge or falling edge. Doesn't matter. We're just going to trigger the ISR. So the period will be so 40 should be used here. So 1 over 40 microseconds will be the frequency of that signal. So you can plug in that number and get into here and calculate x equals to 39. So if you assign this variable, which is in the code, if you look at here, so in the code, I assign that variable to be 39, will give you a period of what for triggering your ISR? Huh? 20. That's a 40 is a period, but in that period, it's going to be triggered for twice, right? Okay, just by looking at your eyes, I know this is a nightmare. Is it? You'll be used to it. And this is just phase one. There's no joystick yet. It's just standing on the table. And I haven't covered how this is being controlled. We're running out of time, but there's another thing. It's pretty hard to understand, but you have to try to understand intuitively. Um, but I think you can imagine. So this is something really being so the mechanical system being controlled by a microcontroller using a PID controller. Even though it's not a airplane, not like Boeing 737 or something. But I think this is a really mini robot can be used in the real world. It's really interfacing with software, hardware, mechanical system. I think this is a really good example of practice. Um, it's better than just program the commercial robots using their GUI. Right? It's touching the bottom level of the hardware, so you know what's going on inside. All right, we'll see you next week.